All right, we looked at aldol condensations, and the conditions that we gave were sodium hydroxide and the removal of water. Realize you can have aldol condensations that are acid catalyzed. They're not as effective because the enol that is formed is not as good as an enolate. It's not as good a nucleophile as the enolate, but it can occur. And the same thing happens. You have to remove water to force the alpha-beta unsaturated carbonyl to form. The products are identical. The only difference is you have acid instead of base. When trying to work an aldol condensation backwards, realize what you're going to do is basically cut the ene in half and take the beta end and make that into the carbonyl, and take the alpha end and make that into a methylene. So let's try some of these. Here we have two aldol condensation products. Try to figure out what reagents were used in order to make them. Okay, to make this, we're going to take the ene and cut it in half. When we cut it in half, this, because the carbonyl is over here, this becomes the methylene group that was the enolate, and this is going to become a carbonyl. What are those two products? We have cyclopentanone and formaldehyde. Excuse me, that's not formaldehyde, that should be acetaldehyde. We're missing a carbon here. My bad. So this should be acetaldehyde, not formaldehyde. Okay, over here, what do we have? We have cyclohexanone and a cyclohexenone with an ethyl on there. How is it that we can make this? Again, cut the ene in half, and you're going to have this be the methylene, and then all the way around, then this will be an aldehyde. Okay, if we look at this, we should have 1, 2, 3, 4. Actually, this would be an aldehyde, so this is going to be an oxoal. 1, 2, 3, 4, 5, 6, 7, 8 will be the length of chain, so octanal, and you're going to have on the 1, 2, 3, 4, 5 carbon an oxo group. So here we go. Octanal, 1, 2, 3, 4, 5, 6, 7, 8. And on the number 4 carbon, 1, 2, 3, 4, 5. Oh, excuse me, 5. 1, 2, 3, 4, 5. Yes, 5 carbon will be an oxo. Notice all you did was cut this in half, turn this into an aldehyde, and turn this into a methylene. This is this carbon. This is this carbon. The carbon that was down here is blocked out was this carbon. This is this carbon. Go ahead and try to figure out what is the product of this aldol condensation. Okay, if I look at this, I have a mixed aldol. This does not have an alpha hydrogen. So this is going to be the nucleophile. This will be undergoing nucleophilic attack. The product that we get is, notice, this is my benzene ring. This was this carbon. This is the connection between here and this carbon. This is this carbon, and this is this carbon. To back this up, notice what you would do is cut here, make that into the aldehyde over here. Cut this, make this into a methylene right there, that methyl group. Now, we're going to go into another type of condensation in which instead of losing water, you are going to lose an alcohol. When this occurs, this is with esters, you have an enolate attack an ester, and what actually happens is you get the alcohol group to leave, and now you form a dicarbonyl, a 1,3-dicarbonyl product. So let's go ahead and look at this. This is going to be something called the Claisen condensation. So again, what do I need to have? I need to have equilibrium formation of the enolate. I don't want complete deprotonation. because if I have complete deprotonation, all of this exists, and they're not going to do nucleophilic attack on each other. So I need to have a small amount of this made, and I do that by using a base that does not completely deprotonate. And I need to have some of this left behind, because now I've got a carbonyl and I've got a nucleophile. So here is my nucleophile and here is my carbonyl. What's going to happen? Nucleophilic attack. Once I have nucleophilic attack, the ethoxide leaves and I end up getting a dicarbonyl compound. Notice, where is this compound? This compound is right in there in the molecule. Well, what part of this compound is over here? That part is right here. And you see what was lost? The ethanol. And it puts it together into a dicarbonyl. Okay, this is a Claisen condensation. Here I'm going to use ethyl acetate, and we're going to treat with sodium hydroxide, sodium ethoxide. Sodium hydroxide would end up cleaving this ester, so you could use it, and it would end up giving you an acid group here instead. But let's just use sodium ethoxide. That keeps the ethyl here. We get partial formation of the enolate. The enolate does nucleophilic attack. We get a tetrahedral intermediate, and the ethoxide leaves, and we end up getting this compound. Now, why? This is all equilibrium. This should all be double arrows. But this reaction actually goes to completion. Well, look what you have present here. Why does it go to completion? Because this is a stronger base than the enolate of this. So this is more acidic than ethanol. So what's going to happen is this ethoxide is going to completely deprotonate this 100%, and this is not going to be existing. The enolate of this will exist, and it can't reverse. You can't have ethoxide come and attack it and undo what just happened because it's already an enolate. So why does the completion go to completion? It's because deprotonation of the dicarbonyl product drives a reaction to completion. The starting ester must have two acidic hydrogens. That should be alpha rather than A. Two acidic alpha hydrogens. Why? Because unless you have two, one forms enolate. The second is the removal of that proton causes formation of the product to be driven to completion so that it can't go backwards. So let's go ahead and look at some examples. Here is another. It doesn't have to be ethyl acetate. It can be any kind of ester. I'm going to do nucleophilic attack. Here I have, once I have nucleophilic attack, I can have the alcohol leave. Notice there is a proton here. The ethoxide deprotonates this and drives it to this. Without that proton here, we wouldn't have it being driven to this enolate, and so reaction would not be complete. You would have just equilibrium formation of everything. That's the most acidic thing in a solution, so the ethoxide forms this rapidly, and the reaction cannot now reverse. So you go ahead and determine what is the Claisen condensation product of methyl pentanoate. So here is methyl, that says ethyl pentanoate, and this should be Me here. My bad, should say ethyl pentanoate. Okay, so here I have ethyl pentanoate, 5 carbons. What's going to be the Claisen condensation? Realize we're going to lose this from nucleophilic attack, and we're going to have the other one right here, add. So what is the product is going to be this. Look at the easy way to figure this out. Cut off the alcohol portion of the ester. Take the carbon that is in the carbonyl and tack it to the alpha carbon in another ester. And you see that is going to be what the product is. So now that you've seen the easy way of figuring it out, determine what is the Claisen condensation product of this compound. Okay, cut this off and tack it on right here. So that's this carbon right here. There's the rest of the compound stuck on. This is just going to take some practice. If you didn't get this, you're just going to have to practice this over and over. And come get help if you're not able to figure it out. You can have a mixed Claisen condensation. If you have two different esters, you can have up to 4 products formed, just like we had with the aldol condensation. But you can have only one product if there's no enolate hydrogen on one, for instance, that it's formyl or benzoyl, and so it can't be doing the nucleophilic attack, or you have one much more acidic than the other. Just the same qualifications as what we had with the aldol condensation. Here's an example. This cannot form an enolate, so this must be the nucleophile. What's going to be nucleophilic? This carbon is going to be deprotonated, and it's going to attack this carbon. So the alcohol portion gets cut off, and so you can see right there, and this gets tacked onto the alpha portion. Notice the ethanol's gone. You can have mixed Claisens on esters with no alpha hydrogens. So we look at formates. That would be an ester of formic acid. Benzoates have no alpha hydrogens. Oxalates, that's 2 acids stuck together basically, is what oxalic acid is. And carbonates, that's an ester that has, that's basically a carbonyl with an alcohol group on either side. Carbonic acid, 1 carbon acid, and then you have ethanols on either side, or some kind of alcohol group on either side. Let's look at some examples. Here is diethyl carbonate. See, it's a carbonyl with alcohol groups on either side. It's like a diester on 1 carbon. There's no alpha carbon. There's no alpha hydrogens. This has alpha hydrogens, so this will be a nucleophile and displace one of these ethoxides. So that leaves. Notice that's the carbon, an alpha carbon. Cut off an ethoxide and just tack it on. And that should be, something's wrong here. Something was cut off. There, I don't know where this, oh. All right, nothing's wrong here. I'm not looking at it completely. The sodium hydride is the base. So what happens is it removes a proton from here and forms hydrogen gas. Okay, again, ethyl benzoate and cyclohexanone. Here we have cyclohexanone and here's ethyl benzoate. Here's our base removing a proton from here. This is going to be the nucleophilic one because this has no alpha hydrogens. This is what's going to be the leaving group. So this carbonyl gets attached right to an alpha carbon, and that's what we see as a product. So now you try to figure this out. What is the Claisen condensation product of ethyl benzoate with ethyl acetate? Well, the first thing that you need to do is write ethyl benzoate and ethyl acetate. Here we go. Here we have a base deprotonating this nucleophile. This is going to be the nucleophilic enolate. No alpha hydrogen. So the ethoxide gets taken off and tacked onto the alpha carbon. That is the product.